Okay, let's get started. Good morning, and today we will study epipolar geometry. This could be a little bit complicated. So let's briefly recap what we studied in lecture 3. So that was the motivation for the camera calibration and image matching that we learned in previous classes. This slide is from lecture 3, and according to multiview geometry theory, if we know camera intrinsic parameters and match a point across multiple viewpoints, then we can lift the multiple observations to a 3D space. That is what multiview geometry theory is saying. And to this end, we study how can we get camera parameters, camera intrinsic extrinsic parameters, which is called camera calibration that we learned in previous class, and match a point across multiple viewpoint. That is what we learned in maybe a couple of times ago. SIFT and image matching, feature matching maybe. That was the motivation, and that is what multiview geometry theory is saying. And epipolar geometry is actually a little bit different thing. So let's briefly recap this one. We learned both camera calibration to get camera parameters and image matching to get coherent points from multiple images. And finally, we can lift observations from multiple images to a 3D space. So if we have these two ingredients, camera calibration and match a point across multiple images, then we can lift observations to the 3D space. That is called triangulation. We will learn triangulation later. Triangulation is not very, complicated thing. Once we have this one, we can just optimize some 3D points in the 3D space. But in practice, so the second one is not very challenging in real world. So the second one, image matching, we used off-the-shelf image processor, right? Off-the-shelf feature extractor like a SIFT or Dino3, anything you can use. But this first one, camera calibration. For the camera calibration, we need to prepare a checkerboard or a 3D object, and then hold the 3D object or checkerboard in front of cameras and rotate myself in front of cameras and capture some images. And then we need to do like a Ji's method or Zhang's method or PMP algorithm to get camera calibration. But in practice, we do not always carry this kind of checkerboard, right? In practice, we do not carry this kind of checkerboard. So this one, the first requirement makes this kind of 3D data collection a little bit hard in real world. So people came up with some smart way that is called epipolar geometry. What if we don't want to or can't calibrate cameras? What if we do not have checkerboard now? Or what if we just use videos or images from internet? They do not have any calibration information. Such kind of cases always can happen, right? So like taking a video with your mobile phone without camera calibration. In this kind of casual setup, not such kind of extensive setup, this kind of casual setup, the answer is epipolar geometry. We can use epipolar geometry to get some camera parameters and lift the images, match a point to the 3D space without requiring camera calibration. That is the good point of epipolar geometry. And epipolar geometry is only about 2 view images, very simple case. And multiview geometry theory, as you can see from its name, multiview geometry theory is kind of superset of epipolar geometry. It covers images, the number of images is equal larger than 2. And epipolar geometry, we will only say relationship between 2 view images, only 2 view images. Of course, we can generalize epipolar geometry to multiview geometry theory, but today we will only focus on 2 view case. There is only 2 view images, and then we will do some mathematical computation, and then and then we lift them to 3D space. without requiring camera parameter, without requiring camera calibration, without requiring checkerboard. We do not have to prepare checkerboard. We do not have to prepare 3D object for the camera calibration. And so let's first see this one. I think this shows some simplified pipeline to get 3D points. There are two cases. The first one, upper one, this one. This one is what we learned in previous class. So far we learned this one. We have checkerboard. Checkerboard means we know 3D measurement of checkerboard, right? We know actual size of checkerboard. We know actual position of checkerboard. Based on this known 3D measurement, we calibrate camera, right? Like Jai's method, Zhang's method, or PMP, anything you can use based on your preference. So that we have camera intrinsic and extrinsic parameter. That is about the camera calibration. We learned this in previous class, right? And let's say we have multiple images, and then we have image matching algorithm. Like we can use SIFT or other features to get correspondence between multiple images. And then we have points from multiple images. And then we can apply triangulation. As I said, we haven't learned triangulation yet, but we will learn this later. This is not very complicated. You just lift them to 3D space. Then we have 3D points. In this case, as we have accurate camera parameters based on known 3D measurement. As I said, the important thing is that checkerboard, we know 3D measurement. We know actual size, actual position of checkerboard. Then we can lift points from multiple images to 3D space without any ambiguity. There's no ambiguity. There's no rotation, translation, scale, ambiguity. There's no ambiguity. We can get metric level 3D points from this combination of camera parameters from checkerboard and match a point from image matching algorithm. That is what we learned so far. Like lecture 3, lecture 4, we've covered image matching algorithm, camera calibration algorithms. But today we will cover a little bit different thing, the below one. Let's say the image matching is the same. We have multiple images, and we have image matching algorithm here, and then we have points from multiple images. That is the same. Points from multiple images. But today we will use epipolar geometry. So we do not need to prepare this kind of checkerboard. We do not need to prepare 3D object. We only have points from multiple images. And then we apply epipolar geometry. This is today's lecture. Then we will get essential or fundamental metrics. Based on this, we triangulate points from multiple images. Based on this essential fundamental metrics, then we have 3D points, but this has ambiguity, up to scale. So here we use checkerboard with known 3D measurement. We know actual position, actual size of checkerboard, but in below case, today's case, we do not have any known 3D measurement, right? So we can still get 3D points, but it has scale ambiguity. Scale ambiguity means so let's say we have images. Let's say we have images of human from different viewpoints. Maybe this is image 1, image 2. If we follow the first pipeline, then we might have person size in the 3D space might be about 1.7 meter, approximately human scale, right? 1.7 meter. But if we follow the bottom pipeline, then what we can get is is up to scale, maybe 10 centimeter, or 1 meter, or 1.7 meter, any scale. So we can't get actual size, actual 3D size of the object. Human usually in the range of 150 to 2 meter, right? So 10 centimeter is, most humans do not have this kind of size. So we have 3D points up to scale. That means if we follow the first pipeline, as we know, known 3D measurements, we have actual size, so that the 3D points of human might have scale of 1.7 meter. This is approximately in the reasonable human size. But if we follow the second pipeline without any known 3D measurement, then we have the lifted 3D human might have size of any arbitrary scale, like a 10 centimeter, 1 meter, any scale. But still, this is very useful because, I mean, preparing this kind of checkerboard is a little bit annoying. We need to print checkerboard. We need to calibrate cameras with calibration algorithms. We need to put checkerboard in front of cameras and capture some images. That is annoying. And in some cases, it is not impossible. Let's say we have images from internet or videos from internet. They do not have any calibration information, so that we can't follow this first pipeline in some cases. So the second pipeline is only option that we can follow. So this kind of, although they have scale ambiguity, it is still widely used and very practical, I guess. So let's get back to the previous slide. If we know extrinsic with camera calibration and checkerboard, this is the first case of the next slide, right? If we have checkerboard, then we can checkerboard with known 3D measurement, then we can get extrinsic with camera calibration parameter, right? This is the case. For example, you calibrate cameras with your checkerboard with known 3D measurement, then you can skip all things we learned today. We learned today is only when we do not have any calibration information. If you can calibrate your camera by yourself with known checkerboard with known 3D measurement, then you can skip all things we will learn today. Just triangulate. Points from multiple images based on your calibrated cameras. That's all. You need to ignore all things we will learn today. But in case we do not know extrinsic, that is today's focus, as I said. What if we can't calibrate cameras? What if we just forgot camera calibration algorithm? Maybe we can forget how to do it, maybe. Or we do not have checkerboard. We do not have any 3D object to calibrate cameras. Then you can follow the second approach, second pipeline. Taking a video with your mobile phone without any calibration or without any checkerboard, then you can use today's focus, epipolar geometry. So we get essential fundamental matrices, and we do not have checkerboard which provide actual 3D measurement. Essential or fundamental matrices might have scale ambiguity. They provide extrinsic information up to scale. And this pipeline shows some difference between what we learned so far and what we learned today. Is it clear? I hope this is clear. Because the followed slide might have a little bit complicated mathematical stuff. So I guess you need to be very familiar with this kind of pipeline. Why we learned today's epipolar geometry? What is difference? At first glance, it looks very similar, right? Getting some camera extrinsic, intrinsic, and lifting them to 3D points. We already learned this kind of things. We already learned matching camera calibration. So why we need to do additional epipolar geometry? So the reason is that sometimes, actually, in many cases, we do not know any calibration information. We do not have access to checkerboard. We do not have access to 3D measurement. So that we often use this kind of epipolar geometry based approach. And multiple geometry theory include all this stuff, all the entire pipeline. The first pipeline, second pipeline, all the things are included in multiple geometry theory. So I will not cover entire full detail and multiple geometry theory in this class, but multiple geometry theory is a governing theory of all this kind of 2D, 3D relationship. Epipolar geometry is just a subset of multiple geometry theory, which is for cases where we do not have access to accurate camera extrinsic. So let's proceed to the next slide. So the reason why we consider multiple viewpoints, and this slide shows why we consider multiple viewpoints. What if we can just use, why don't we just use a single viewpoint? Single viewpoint is much simpler and easy to get, right? But the reason is that there is a depth ambiguity. As I said, 2D image is just a projection of 3D world, right? That it means it loses some information. So 3D to 2D, there's no ambiguity. As long as we have camera intrinsic and extrinsic, we can just project or render them to the 2D space. There's no ambiguity. That is about computer graphics. But 2D to 3D, 3D geometry recovery, 3D reconstruction from image, If we have only single viewpoint, single view image, then it already loses z-axis information, right? So this shows depth ambiguity, the most common ambiguity when 2D to 3D reconstruction. This black line is the image plane, and let's say we have this kind of measurement in image space. We capture image, then we have this kind of measurement in image space. But actually, infinite number of 3D geometry can produce the same 2D image. As you can see, this orange line, the first orange line can produce the same looking image. Second orange line, third orange line, all the orange line have different 3D geometry, but they produce the same 2D image. That is depth ambiguity. So there's a z-axis in camera coordinate system. Camera coordinate system, z-axis is a raised direction, right? Z depth, and so this called depth ambiguity. We can't uniquely determine depth of 3D object given only a single view 2D image. And this shows, I remember I showed you many tricky examples of this kind of distortion. So this person and this tower has very far distance, right, in 3D space. We know this actual size of this tower. So this tower might be very far away from this person. But from this image, maybe this tower is not a real tower that we know. Maybe this tower has a very small size. So we can differentiate between the cases where this tower is very close to human or very far from human and very, very big. So we can differentiate such cases, and that means depth ambiguity. And because of depth ambiguity, or there are many cases, scale ambiguity, and there are many ambiguities, occlusion, many ambiguities. So that makes single view-based 3D reconstruction in theory impossible, in theory. Of course, these days we have lots of learning-based modules which simply reconstruct 3D object, 3D scene, 3D human from a single image. We already have it, but in theory, in particular, according to multiview geometry theory, we can't, in theory, can't recover unique 3D geometry from single image, single view image. We will cover this kind of learning-based systems which can reconstruct 3D geometry from single viewpoint image later, maybe after midterm. But until midterm, we will focus on some fundamental theory and why we learned this. So we have epipolar geometry, the geometry of stereo vision. Stereo means there are some two. There are mono and stereo. Mono means one, stereo means two. So we have two cameras, two images. Stereo vision means we have two images. So we have like a monocular. It means single image, or this just some different things. So monocular image, it means single image. Stereo vision means there are two images. So given 2D images of two views, what is the relationship between pixels of images? Can we recover 3D structure of the world from the 2D image? That is about epipolar geometry, right? Without accessing to accurate camera calibration result, let's say we do not have actual camera calibration, camera intrinsic, extrinsic. Only we have, what we only have is a match point across different images from different viewpoints. Then in this situation, very practical setting, how can we get relationship between pixels? How can we recover 3D structure of world from 2D images? That is about epipolar geometry. The epipolar plane is defined by two camera centers and 3D points. This is camera center 1. So let's say we only consider two view images, and there's this first camera center, the second camera center. Of course, they are, the relationship between two cameras are explained with camera extrinsic, R and T. And we have 3D points, X, and epipolar plane. Epipolar plane is like this one, gray plane. So there are, we will study detail later, but this is 2D projection of the second camera. This is the 2D projection of the first camera, and we have some 3D point X, and then we have 3 points, right? Camera center 1, camera center 2, and some 3D points. Then we have 3 points, then we can determine a unique plane, that is epipolar plane. A plane consists of camera center 1, camera center 2, and 3D plane, 3D point. That is epipolar plane. So epipolar plane is defined by 2 camera centers and a 3D point. That's that we have 3 points that we can uniquely determine a single plane. That is epipolar plane. And its intersection with an image plane gives the corresponding epipolar line. I guess, so we have this epipolar plane, and we have image plane, right? This image plane, and then intersection between this plane, and this image plane is, let me change the color. This one, this blue line, is a intersection between epipolar plane and image plane, right? That is epipolar line. That is called epipolar line. So there are many new terms. It might be a little bit confusing. Epipolar plane is a plane consists of 3D point and 2 camera centers. An epipolar line is a intersection between epipolar plane and image plane of each camera. That is in epipolar line. And epipole is a E. There are 2 E's, right? So we have 2 images from 2 different viewpoints, and then we can make a line between 2 camera centers. This C1 and C2, we can make a line between them, like this line. And then we have intersection between this line and each image plane, that is epipole. The epipole is the projection of one camera center onto the other camera's image plane. This is the same thing, right? It's intersection point of all epipolar lines in an image. So there are 3 new terms. Let's recap this one. Epipolar plane is a plane which is uniquely determined by a 3D point X and camera center of 2 images. That is epipolar plane. We have 3 points that we can uniquely determine a single plane. That is epipolar plane. An epipolar line is a intersection between epipolar plane and image plane of each camera. That is epipolar plane, the blue line. This is epipolar plane, epipolar line. And epipole is we can make a line between 2 camera centers, and then we can get intersection between this line and image plane of each camera, like E and E prime. They are epipole. So we have 3 new terms. And so that is just a definition. And why they matter? Why we define such kind of complicated lines, points, and plane? So if we know intrinsic and extrinsic parameters of 2 cameras and to the image position of a point, like let's say these images are taken with different viewpoint. They have some rotation and translation between 2 cameras, and we have this line, this point, and epipolar line of this point is this line. So what does this mean? So we have intrinsic and extrinsic parameters of 2 cameras, and to the image position of a point in one camera, then the corresponding epipolar line is the blue one. In the other camera defines the locals is the location of all potential 2D position where the point could appear. So depending on the size and position of the 3D object, the potential 2D positions of this point in this viewpoint, that is the semantic meaning of epipolar line. I guess this might be a little bit confusing. Let's say we have 2 things. Let's say we know intrinsic extrinsic parameters of 2 cameras, and then we know 2D image position of a point. This is the point that we know, and the corresponding epipolar line is this one, this highlighted one. in the other camera defines the locations of all potential 2D positions where the point could appear. Depending on the 3D position and 3D size of the 3D object, this object, only possible, this point always appear only on this line. This point cannot appear this line. This point cannot appear this position. This position, the same meaning 3D point is always projected to on the epipolar line, only on this epipolar line. Make sense? So this one and this one are matched, but depending on the size of the 3D object and position of the 3D object, this one could appear in this one or this one. So this point, let's say this denote A, and this is image 1, image 2. This is A1, this is A2, or A2, 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 A2. We can define a single 3D point on the 3D space, and this is just a projected position of the 3D point. Let's say we call this A1, and of course we can project the 3D point, same 3D point to the second image plane. Then possible position of 3D point A on the image plane of the second camera is always on this line. A2 cannot exist on this. No. A2 cannot exist on this plane. A2 always exists on this line, on the line. That is semantic meaning of epipolar line. So epipolar line, the other camera defines. That is the reason why we have this sentence. Location of all potential 2D positions where the point could appear. That is the semantic meaning of epipolar line. We will see it later, but this is quite useful. Maybe we can, so based on epipolar line, maybe we can, we need to make a correspondence between this position and this position. Then, let's say, then we can reduce the search space of the image matching. We do not have to search entire image. Let's say we have this point. We want to make a match point with this point, with this A1 from this image. Then what the search space is reduced to only epipolar line, because the possible projected point of this 3D point A is always on the epipolar line, right? So we do not have to search this region. We do not have to search this region. This A will always appear on the only on epipolar line. So we always need to search only on epipolar line without considering these regions. We can exclude all these regions. Only consider point on the epipolar line. When we find a match point, right? So that is actually a good point of epipolar line. From this slide, we will see how we can do this later. But from this slide, I encourage you to be familiar with the semantic actual meaning of epipolar line. So epipolar, in mathematical way, epipolar line is just the intersection between epipolar plane and image plane of each camera. That is epipolar line, right? But what it actually means is that possible, locations of all potential 2D positions where the point could appear. That is the actual meaning of epipolar line. Is this one? Let's say different cases. So, and this is point B. This is point B, and B always appear on this plane. This B1, this B2, 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 B2. Possible position of B, let's say we have 3D point A, 3D point B. We can project them to different image planes. Then B can be projected, of course, projected to the second image plane. Possible position of B on the second image plane is only on this line, epipolar line. The same things as well. If we use this one, C1, then this is C2, 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 C2. We have 3D point C on the 3D space. And then we can project C to the first image plane, second image plane. Let's say this is C1. But possible positions of C on the second image plane makes this epipolar line. And C could appear only on this epipolar line. It can't exist in this region, right? That is actual meaning of epipolar line. So let's recap some several terms that we've learned. Baseline, this is called baseline. Baseline, the yellow line. A line between two camera centers, O1 and O2. This is called baseline. And epipolar plane, we learned this, gray plane, defined by a 30-point P and camera center of two camera center, O1 and O2 contains baseline and P, right? That is a epipolar plane. And epipoles, as we learned, is a intersection between image plane of each camera and baseline. That is epipole. And epipolar line, blue line, is the intersection of epipolar plane with the image plane of each camera. That is epipolar line. It might be a little bit confusing, but I guess you need to, once you get familiar, I guess there will be no very complicated things. So the baseline is a yellow line, which is a line between two camera centers. And epipolar plane is a gray plane defined by 30-point P and two camera centers. And epipole is a point, intersection between baseline and image plane of each camera. That is epipole. Epipolar line is the intersection between epipolar plane and image plane, the blue line. So there are four terms. I guess there will be no more additional terms. You don't have to be afraid. Baseline, epipolar plane, epipoles, and epipolar line. So now we will get back to our original goal. How can we get relationship between points from different viewpoints without knowing accurate camera parameters? That was our original goal, right? Relationship between corresponding image points. How can we get this? There could be a little bit mathematical stuff. The word reference system aligned with the left. Our assumption is that we can define word coordinate system with our preference, right? So we just said left camera is a word coordinate system, and then right camera has a orientation R and offset T. So and then we use so that the matrix M is a multiplication between intrinsic and extrinsic, right? So left camera, as we define left camera as a word coordinate system, its extrinsic becomes identity matrix, right? So and right camera M prime is a multiplication between K prime and RT. And then this one, the small p is a multiplication between large MP. So we first apply extrinsic to transform word coordinate system to camera coordinate system, and then apply K to transform camera coordinate system to image coordinate system. Then we have image coordinates, right? P prime as well. We have image matrix M from this one, and we have the same 3D point P, and then we apply M prime. Then we have P prime here, P prime P, which is a column vector U prime V prime 1 in homogeneous coordinate system. That is just a camera. I mean, we learned in homogeneous coordinate or camera calibration, right? Just a relationship between word, camera, and image coordinate system. So based on this thing, and then we'd like to know P prime in world coordinate system, that is this one. So P prime here, right? P prime is a, P prime is here, and then we can just apply simple math. The camera P prime is a camera coordinate system, right? P prime is where x is what we want. P prime in word, right? P prime is Rx plus T, where x is what we want. Then we can just P prime minus T, R inverse equals to x, right? But rotation matrix is orthogonal matrix. That means R inverse equals to R transpose. So that we can simply rewrite this one to R transpose P prime minus T. That is world coordinate position of P prime. And O2 in world coordinate system. O2 is here. It's the same. So in camera coordinate system, the camera center is always 0, right? Camera coordinate system, and R x plus T, where x is O2 in word, right? So that we can just rewrite this one, T equals to x, it goes to here. R is an orthogonal matrix, so inverse and transpose is the same. So minus R transpose multiplied by T, that is a O2 in world coordinate system. It's just a matrix multiplication and subtraction. And then normal vector of epipolar plane. We learned epipolar plane is a plane which consists of P, O1, and O2, right? This plane. Normal vector might be in this direction. So we can apply, so we have 2 points on the image, right? The 2 points on the plane. P prime, we know P prime in world coordinate system. O2 in world coordinate system, we already know this, right? So, and this is origin in world coordinate system, right? So then we can make a cross product to get normal vector, right? We have 2 vector. We have 2 vector. This O1, O2, P prime. We already know these 2 vectors, right? And P prime, O1, O2 are just on the same epipolar plane. Then we can get normal of epipolar plane by cross product. Just cross product these 2 vectors. That is the normal vector of epipolar plane, this one. Right? And then, so that is the normal vector, right? Just the cross product between 2 vectors. And O1P, this, let's use different color. O1P, this one. This vector lies in the epipolar plane, right? So the dot product of the normal and epipolar plane is 0, right? O1P is on the epipolar plane. And dot product between this normal vector and O1P should be 0 because, normal vector is always perpendicular to any vector on the plane. So that we have this one. O1P is just a P, right? This is a normal vector. So the dot product between these 2 vectors should be 0. Just the dot product, A transpose B, dot product. I guess there's no very complicated thing. Just matrix multiplication and cross product and dot product. And we rewrite this one, we get this term. And then we learned this. We know cross product, right? We know cross product, and we can rewrite this one as like this notation. So this, from this the dot product between O1P and normal vector should be 0. Then we can rewrite this term right like this, and then we can. There's a cross product, so we'd like to rewrite this cross product part with this one. Oh, sorry. This one based on this notation. So the cross product between two vector is just this matrix and vector v. We can notate by this convention. And this matrix, this matrix is a skew symmetric matrix whose rank is 2. Skew symmetric matrix means, you're familiar with skew symmetric matrix? It's A transpose equals to minus A. That is skew symmetric matrix. Anyway, so we can rewrite this term like this, and then rewrite this one like this, right? Just apply just transpose, just change the order. So that finally we reached here. A little bit of complicated stuff, but we finally reached here. That is the important thing. The final conclusion. So now we have relationship between P prime and P. So finally, we have relationship between P prime and P. P prime is a position in the 2D image space of this camera, and P is a 2D image position of this camera. And then we define this one, the skew symmetric matrix of translation and R as essential matrix TE. So finally, we have this equation, P prime transpose E P equals to 0, this one. Finally, so P prime is just a 2D position of a first camera. P is a 2D position of the second camera. And this is some matrix, which is called essential matrix, right? So finally, we've here, P prime transpose E P equals to 0. And E is called essential matrix. Establish constraint between matching image point. Determine relative position and orientation of two cameras. It is 5-degree freedom up to scale. So E is a multiplication of skew symmetric matrix of translation and R. So originally it should have 6-degree freedom. Rotation has 3-degree freedom. We are in 3D space, right? So we can rotate in 3 directions. So it might have R is a 3-degree freedom. Translation, we can move in the 3 directions. So it has 3-degree freedom. So in total, it should have 6-degree freedom. But it doesn't matter if we apply lambda, any lambda to this equation, it doesn't matter, right? Lambda can be 1, 2, 100, anything. That means, we can plug in then P prime transpose lambda E P equals to 0. So lambda E, we can uniquely determine E. It is scale ambiguity. Lambda can be 1, 2, anything. So E can be determined up to scale. I guess you heard up to scale this one, right? We talk up to scale stuff in the first part of this lecture. Epipolar geometry has up to scale ambiguity. So that is from here. We have up to scale ambiguity. We can determine unique E because we can multiply any lambda, any scalar lambda. Lambda can be 1, 2, anything, any scalar is possible, right? You can multiply lambda with the same side, right and left side, and lambda can be 1, 2, or anything, so that we cannot uniquely determine essential matrix E. So E has a 5-degree freedom, because in total 6, and then we have scale ambiguity -1, so that you have 5-degree freedom. That is the reason why we have scale ambiguity in epipolar geometry. We can't uniquely determine E, right? And this is called essential matrix. There was so far a little bit complicated mathematics stuff, but it's just some cross product, dot product, and matrix multiplication. Just the relationship in 3D space. And finally, we have this equation. This is the conclusion. And we call this the skew symmetric multiplication between skew symmetric matrix of translation and rotation is denoted by E, essential matrix. And the property of essential matrix is that the meaning of the essential matrix is that it has established constraint between matching image points and determine relative position and orientation of two cameras, and has 5 degree of freedom. Originally, it should have 6 degree of freedom, but as you can see, we can multiply any lambda so that it has scale ambiguity. So we subtract 1 so that we have 5 degree of freedom. It's okay. A little bit, maybe. Anything unclear is okay. If you have any question, you can ask any question. No. I think this is a little bit difficult and complicated, but you can. I mean so that you can just see the detailed derivation of this equation. But there is no complicated stuff when driving this equation. Just these are what we learned, right? How can we convert chiral coordinate system to world coordinate system? We can just use extrinsic to get world coordinate system position. This is just the same one. I mean, just converting chiral coordinate system to world coordinate system, and then normal vector is just right, the high school math. We can just apply cross product between two vectors on the same plane to get normal vector, and then dot product between any vector on the plane and normal vector should be 0 from this one, and then we can just rewrite this, keep rewriting this, keep rewriting, so that we finally reach to this one, P prime transpose E P equals to 0. That is about essential matrix. But so I forgot to mention this. So when calculating the essential matrix, we assume that we use canonical cameras. That means intrinsic of two cameras is just identity. They do not have any information. They have the same intrinsic, and they do not have any special values, just identity matrix, so that we only consider extrinsic when calculating essential matrix. But in real cases, of course, the K might not be identity, K prime might not be identity. It's just that is the reason why we call this essential matrix, minimally necessary but not perfect information. That is the reason why we call this essential matrix. Then we learned two matrices at the first, right? Essential matrix and fundamental matrix, right? We learned two matrices. Then it's time to see fundamental matrix. And this is about fundamental matrix. This is the essential matrix. If we include intrinsic of different cameras, then we get this fundamental matrix. I will not show detail, it's too complicated, but you can just plug in intrinsic in this equation, in this derivation, so that we can get fundamental matrix. We can get fundamental matrix with this one. So this is essential matrix. From its name, we can know that essential matrix is just minimally necessary information, excluding all the intrinsic, just only consider extrinsic. So that is essential matrix. And it says relationship between 2D points. This is 2D points, 2D points from different viewpoints. It says some relationship between these 2D points from different viewpoints. That is about essential matrix without considering the intrinsic. But in real world, we of course need to consider intrinsic, right? So that is about fundamental matrix. Fundamental matrix. So this shows the comparison between essential and fundamental matrix. Similarity is that both relate the matching image points, encode epipolar geometry of two views, camera parameters, right? It encodes extrinsic between two cameras, right? Here as well. But difference is that essential matrix encode only camera extrinsic parameter. We assume K equals to K prime equals to identity here when getting essential matrix. But in fundamental matrix, it also encodes the intrinsic parameter, right? Here K prime minus transpose K inverse, we have this, right? So additionally consider intrinsic parameters closer to real world cases. But starting from fundamental metrics, it makes things too complicated. So you can start from essential metrics, and then once you get essential metrics, you understand essential metrics, you can just expand your knowledge to fundamental metrics. And the properties of fundamental metrics is that, so in essential metrics, we learned the property of essential metrics. This is the meaning and 5 degree of freedom, right? We originally should have 6 degree of freedom, but it has scale ambiguity, so we subtract 1 so that we have 5 degree of freedom. But fundamental metrics, it has 3 by 3 matrices, homogeneous coordinate system, has scale ambiguity, and so the rank is 2. Because these skew symmetric metrics always have rank 2. So we always follow minimum rank of the matrix when doing the matrix multiplication. So the rank of fundamental matrix is 2, and so that the degree of freedom of fundamental matrix is 7, because 3 by 3, 9 minus 1, because we do not have full rank. We have only rank 2, and has scale ambiguity, so that we have 7 degree of freedom for the fundamental matrix. Essential matrix, it has 5 degree of freedom, but fundamental matrix, it has 7 degree of freedom. And we will see this picture later. We'll see this. Yes, we will see this one later. Okay. So with this very long, complicated stuff, so why we do this? How can we use this? In which case this is useful? Given 2D point on one image and fundamental matrix, let's say we have image 1, image 2, and we have some point, and let's say we have fundamental matrix, then we can make epipolar line, right? Epipolar line from this one. If we know P, epipolar line is Fp. If we know P prime, epipolar line is F transpose P prime. We can get epipolar line. So you can see this image, this example. From this image, this point, and we know fundamental matrix, then we can get epipolar line, like maybe this line, so that when we find correspondence, matched point between different images, we only need to consider only this line. We do not need to consider this line. We can exclude all this region. We can exclude all this region and then only consider this epipolar line, so that image matching's accuracy becomes much better, because we can get rid of all the false positive matching. We can always only consider points on the epipolar line, so that the image matching accuracy becomes much better. That is the benefit of fundamental metrics. If we get fundamental metrics, then we can make epipolar line from any points on the image 1, so that any epipolar line from image any point, so that we can reduce the search space. Where is it? Yes, we can reduce the matching space. We do not need to we do not need to consider entire region of the image. We always need to only consider points on the epipolar line, so that we can make the image matching result much better, because we can, and maybe much more efficient, because we do not need to consider all regions in the image. We only need to consider points on the epipolar line, so that image matching accuracy, image matching speed becomes much better. That is the good point of fundamental metrics. And fundamental metrics, it provides the relationship between points from different viewpoints. As I said, without accurate camera extrinsic, without recurring camera parameters, without checkerboard. That is the good point of fundamental metrics. Then how can we get this? This is so this is not very complicated, I guess. So we already have relationship between fundamental metrics and different points right? So, I mean, we already have this equation, so we can rewrite this one like this. Let's say pi is a ui vi 1 and pi prime is ui prime vi prime 1. Then you can rewrite this equation with this matrix multiplication form. And we know we need 8 points. So if we have 8 matched points, then we can get fundamental matrix, so that we can use this fundamental matrix to get epipolar line of any points. So we learned F fundamental matrix F has a 7-degree freedom. But I told that we need 8 points. So maybe we can use 7 points. 7 points could sufficient. In theory, yes, we can use 7 points. But F is just the 3 by 3 matrix. That means we need 9 equations, right? In theory, 9 equations. But if we use rank k equals to 2, then we can reduce 1 equation. So 9 minus 1. And then we can additionally use this one. Determinant of fundamental matrix F should be 0. But it is not full rank, so it is determinant is 0. Then we can reduce 1 more equation, so that we can use 7 equation. But the problem is that determinant it brings us cubic equation. So there could be more than 1 solution, nonlinear equations, so much more complicated and unstable. So in theory, we can use 7 point. So out of 9 equations, we can use this rank equals to 2 to reduce 1. And determinant should be 0 to reduce 1, so that we can use 7 equation in theory. But determinant gives us cubic equation, which is nonlinear, and could give us more than 1 solution, so it's a little bit unstable. So we simply use 8 point. And then how can we do this? We just use singular value decomposition to get fundamental matrix F. And this shows, so this picture is what we saw in previous slide. This is just if we do not, so this shows the difference. Left is without constraint rank equals to 2. The rank of fundamental matrix needs to be 2, right? Because skew symmetric matrix has a rank 2. But without using this constraint, as you can see, the epipolar line do not converge to a single point. But, so we need to use constraint rank equals to 2. So this is essential. As you can see, without this constraint, we get quite unstable fundamental matrix. So we can, when doing single value decomposition, we use rank equals to 2. But that's the end for today, I guess. But today's stuff might be a little bit intense. So, but I encourage you to first get to know why we learned this. That's why we learned this. So, in previous lectures, we studied image matching and calibration. Calibration requires checkerboard, but that is not always happening. We often do not have checkerboard. We do not have access to camera parameters, so that we need some more practical solution. That is of epipolar geometry. Without using checkerboard with known 3D measurement, we'd like to use we'd like to get some solution up to scale, although it has some ambiguity. We'd like to get solution, and that is about epipolar geometry, to get essential and fundamental metrics. The output, at least for today, the output of epipolar geometry is only essential metrics and fundamental metrics. That is our interest. And this is your motivation why we need to use 2 viewpoints, although some recent learning-based method can handle only single viewpoint image. And there are some, and this shows the actual meaning of epipolar line. Location of all potential 2D positions where the points could appear. these are 3D. We have 3D points. We can project the same point to this position, and then given this possible position of this point is always epipolar line. And there are some new terms like baseline, epipolar line, epipose, and epipolar line. The baseline is a line between two camera center. Epipolar plane is a plane consists of 3D point and camera center. And epipole is the intersection between baseline and image plane. And epipolar line is the intersection between epipolar plane and image plane. And then we derived essential metrics with this simple math. We change them to all the world coordinate system, and they get normal vector. And then the O1P should be on the plane, so the dot product between them should be 0. We rewrite this, rewrite, and then we get this famous equation, P prime transpose E, P equals to 0. And this is the essential matrix. But we can uniquely determine essential matrix because it has scale ambiguity, as you can see from here. So it has 5 degree of freedom out of 6 degree of freedom. We have scale ambiguity, so we reduce 1 so that we have 5 degree of freedom. But the essential matrix, from its name, we can know this as the minimally necessary matrix without intrinsic. So we'd like to include intrinsic in fundamental matrix so that we get this one. And fundamental matrix is, 3 by 3 matrix, but rank should be 2 because skew symmetric matrix, this is skew symmetric matrix. This is always rank equals to 2. And we take minimal rank when doing matrix multiplication, so that rank equals to 2. So we subtract 1 and scale ambiguity subtract 1 so that we have 7 degree of freedom. So why we do this? Because we can get epipolar line from a single 2D point. Once we have fundamental matrix F, we can get epipolar line of this point. So that we can, when image matching, we can only include this line. When finding matching of this point, we can only consider this line without considering all the other regions. That makes image matching much more efficient and accurate, right? And we need a point. In theory, we can use 7 point because fundamental matrix degree of freedom is 7. But to make it 7, we need to use this constraint. So that makes a cubic equation so that it makes a little bit unstable because it's nonlinear and more than one solution. So we simply use a point. And then we use singular value decomposition to get fundamental matrix based on this equation. And rank 2 is necessary, as you can see. Without rank 2 constraint, we get diverging fundamental matrix. Okay, so this is today's focus. Anything is unclear? Any question you have? It's okay. And as you might get notified, you have assignment for the camera calibration. You need to make us some print. You need to print checkerboard, and then you need to using your own camera. Any camera is okay. Use your mobile phone, tablet, anything is okay. Compare your camera calibration and OpenCV's result. That is the assignment. Anything is unclear about assignment, you can ask anything.